Eo. We wait a while hả? Okay. Meow. Đây, go up. Phí mà. Okay. Others a while hả? Draw again. Just now I draw from the back, mà right? Okay, this is the galvanometer. Okay, okay, north to south. Then the movement of the, it will be here. Okay, it will be here. Okay, so, okay, see here. Okay, so according to the Lenz's law, okay, the direction of the induced current always is opposed of what we have learned of the motion, okay, that acting on the solenoid. Okay, so if you see here, okay, just now I say the answer is left hand side, my right? Okay, okay, most of you here already. Yes, okay. So if let's say it's moving the permanent magnet is moving into it, is moving into the solenoid. So which means that this part, it will be North Pole. Okay. In the those that is on the mic, please off the mic, because there I think there's some disturbance here already. Okay. So you have moving into is same polarity. Moving out, it will be different polarity. Okay, so since it's moving in, this part is North Pole. So which means that this will be south, north and south. So then you use your right hand grid rule to identify the direction of the current in this part. Okay, so north to south, north to south, north. This part, this finger always point to the north part. So this one, can you tell me the arrow in this part should be going down or going up? Going down or going up? Down, correct. So it's going down, 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 down. So which means that this part is going up, this part is going down. So the flow of the the current, it will be from here to here. That's why your pointer of the galvanometer is towards the left hand side. It's towards the left hand side. Okay? Can get it here or not? Because here the current is coming down here, then up here It's a circuit. Circuit, the current must flow in a closed circuit one, in a complete direction. Okay? Shamima, can follow here? Why always got sound one? Nazifa, your mic is on. Okay, good. Others? Never mind, it's okay. Shamima can already, Okay, no problem here, Okay? Never mind, it's okay. Okay, so finish. Okay. Mama. Okay. So this is how you use the Lenz's law to identify the direction of the induced current in the solenoid. Okay. So, okay, this one you see here. This one is going. Okay, is going in. So which means that this part is north. This part is south. Okay, this part is north. This part is south. That's why you see here. North pole, south pole. So the current is going down. So it's correct over here. Okay. Okay. So likewise, if let's say this one going out, this one going out. So which means that this part is north pole or south pole. Okay. South, correct. It's south. Okay. So it's south. So which means that this one south, this one north. So you are using your right hand grip rule, following the pointer at the north pole there. So the current is going up in this part. So this one correct already, no? Okay, here, if let's say here is the south pole, okay, we also using the same rules, okay? So now this one south is going out. South is going out. So which means that this part is, yes, correct. It's in a different polarity already. So then you use your right hand grip rule, okay? So the current is going down. So this one is correct as well. Okay, so the last one. Okay, the south is going in. South is going in. So if let's say it's going into towards each other, so this part is the same polarity, correct? It's a south. So this one is north. So using like this, the current is moving up in the solenoid. So it's also correct. Okay, remember, towards each other, or in another words, the magnet is going in, then the solenoid, the end part of the solenoid is in the same polarity as the magnet. If let's say it's going out, then the end part of the solenoid, it will be in a different polarity as the magnet. Then after that, once you identify the polarity, then you use right hand grip rule to identify the direction of the current, the direction of the current. Okay? Can follow here? Can I? Okay, so next. Okay, so can you tell me what is the answer here? Why so fast one? B. C. Okay, so C. Angeline, so fast change already. Okay, correct. The answer is C. Okay, the answer is C. Okay, so why is it so? You see, this one, the direction of the magnet is going into the solenoid. Going into the solenoid. So if let's say it's going into the solenoid, so which means that it is the same polarity as the magnet. Okay, the end part here. So this one north, then this one it will be south. North and south. Okay, so the answer it will be C. Okay, very good. Okay, so most of you can understand well about the Lenz's law already. Okay, so we have learned about the electromagnetic induction in the wire and also in the solenoid. Okay, so next. Wait. Correct, the answer it will be C. Very good. So most of you can understand it well already. Okay, so now, okay, we will use a law, okay? we call as Faraday's law. Faraday's law, okay? So, actually, where is the Faraday's law? Where is my Faraday's law? Okay, here. Okay, so this one, I want you to copy it down as notes number 6. Okay, whole thing here. Number 6 for whole thing here. Okay, so the magnitude of the induced current, we will identify following a law we call as Faraday's law. Faraday's law. Okay, so what is Faraday's law talk about? It states that the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux or the rate of the cutting on the magnetic flux. Okay, so which means that the faster you cut the magnetic flux, the greater the magnitude of the induced current. So this is what the Faraday's law are talking about. Okay, so for straight wire, the induce of the EMF, or we call it as induced current, can be increased by increasing the speed of the motion, which means that the straight wire you are moving, you move faster. Okay, you move faster. You move faster, then it will cut more frequent, then it will produce the greater magnitude of the induced current, or increasing the strength of the magnetic field. How can you increase the strength of the magnetic field? We have learned before in 3.2 already. How can you increase the strength of the magnetic field? Okay, for induced EMF, what is the magnetic field? Okay, correct. What is the magnetic field here? Is the magnetic field by the permanent magnet. Correct. What Jayen say is that either put the magnet use a stronger magnet. Correct. Put a magnet closer, or correct. Okay, like what Kersing said. Very good. Okay, you put 2 pairs of magnet. Okay, 2 pairs of magnet to increase the strength of the magnetic field. Okay, so now it's in a straight wire. How about solenoid? You think about it and see. When you are copying this notes number 6, you think about it. In solenoid, how can you increase the magnitude of the current, induced current? Number of turns in where? More. Correct. Number of turns in where? In where? In the coil, in the solenoid. Correct. Can? No. Correct. Okay, in the solenoid. Other than that, actually it's also about the same as the straight wire, increase the speed of the motion, means that you move more faster of the permanent magnet into the solenoid. Okay, into the solenoid. Okay, other than that, you can use a stronger magnet, okay, to increase the magnetic field. In another way, you can increase the magnitude of the induced current. Okay, can I continue already? Finish copying? Finish copying? Not yet. I give you another 2 minutes to do so. 2 minutes. Hopefully by before the end of MCO, we can finish chapter 3. Then after that, when school reopen, we will go for chapter 4 already. until flux, right? No, a straight wire also need the whole thing. The whole thing. Okay? Sorry lah, like this lah. Okay? This one is number 6, then this one is number 7. Number 6 and number 7. Okay? So if let's say the definition of electromagnetic induction, usually we won't use the cutting of the magnetic field light. We will say that the cutting of the magnetic flux. Okay, cutting of the magnetic flux. Okay, can? Finish? Finish? One more minute, ah. Okay, I continue already, ah, because we still have a little bit left. Okay. Okay, so this is notes number 8. Okay, for the solenoid. Okay, for the solenoid. Okay, the induced EMF can be increased by increasing the speed of the relative motion. Means that you move faster the permanent magnet into the solenoid, increase the number of turns. Very good. This is what you have, or some of you can have told me just now, or use a stronger magnet, or use a stronger magnet. Okay, use a stronger magnet. Actually, one more you can talk about is the thickness of the wire, the thickness of the wire. Okay, because if let's say the thicker the wire, you are having a lower resistance. Lower resistance, then it will produce a greater induced current. Okay, greater induced current. Okay. Okay. Done. Done. Ah. I'm sure this one is Jayen. Okay, done. No, not you, Megan. Angeline, you learn already. Okay, done. Right. I think it's Megan. Okay, bye. Come next. Done. Okay. So this is the, if let's say, okay, if let's say experiment is coming out using electromagnetic induction, they are using the factors, okay? For example, the speed of the magnet, the number of turns, the strength of the magnet, of the resistance. Okay, this can be your magnetic variable, manipulated variable, and the induced current is the responding variable. Okay, so the induced current can be measured by using the galvanometer. Okay, so the greater the speed, the greater the induced current. Then the fixed variable can be the number of turns, the strength of the magnet, or the resistance of the circuit. As I said just now, is the maybe it will be the wire is the one that affecting the resistance of the circuit. Okay, can okay? So this one I don't think you need to copy down. Okay, but if let's say the school reopen, I will let you see I will try to show you a experiment related to this electromagnetic induction, because until now, for the past few years, okay, they don't come out the experiment related to this electromagnetic induction. So maybe high chance it will come out this year lah. So that's why maybe after school reopen, I will show you. Okay, I don't think we are able to do any experiment because of social distancing. Okay, but I will show you in I will show you in the class lah. Okay, can Okay, so the rotation of the application of the electromagnetic induction. Okay, so for example, you know, pasar malam, okay, or pasar pagi. Okay, you especially in pasar malam. Okay, so the environment is dark one, but they will need a light to let the customer or to see their products or to buy something. So they need to have something, a current to produce the electricity to light up the bulb. Okay, so that's why this comes to the generator. Okay, the generator. Yes, the bissing thing. You pull already, that one is actually the generator. And generator is using the application of electromagnetic induction to induce the current. Okay, then it will produce the electricity to light up the bulb. Okay, so why is it we say that it is using an electromagnetic induction? Okay, this is what is inside a generator, a simplified one. Okay, a generator. You have a bar magnet. You have magnet here, permanent magnet here, and this is the coil. The coil, when it turns, okay, when it turns, it will cut the magnetic flux between this permanent magnet, and it will induce current. It will induce current. Okay, it will induce current. So we have two types of generator. Okay, one is DC generator, and one it will be AC generator. DC generator and AC generator. Okay, can you tell me in these two diagrams, what can you see the difference between DC generator and AC generator? The left one is the DC generator, and the right one is the AC generator. Okay, the DC stands for direct current. Okay, cube. Where's the cube? Where's the cube? Where's the cube? Galvanometer, no. Both also is this. Okay, voltmeter and galvanometer. Okay, one use commutator. Okay, cuboid. Correct. Very good. Okay, thank you for giving me so many loves. Okay, I know you need love a lot nowadays. Okay, because stay at home too long already. Okay, right. Correct. What Xing Yi and Jayen say is correct. Okay. Okay. Right. So you see here, cube one look like cuboid. One look like cube. One look like cuboid. Okay, never mind. I explain here first. Okay, so DC here. Okay, DC here. DC here stands for direct current. Direct current. AC here stands for alternating current. Alternating current. So one of the generator is producing direct current. One of the generator producing alternating current. Alternating current. Okay, so the difference between direct current and alternating current is direct current, the current only flow in one direction. Flow in one direction. Alternating current is the current flow in alternate direction. Means that it can flow from left to right, then The other one flow from right to left. Okay, but from direct current only left to right, left to right, left to right like that. Okay, so what makes these two generator difference in producing direct current and alternating current is the commutator. Okay, the commutator here. So this thing in both DC generator and AC generator, we will call it as commutator. Okay, commutator. Okay, so this in the direct current, we will call this the commutator is split ring commutator. Split ring commutator. And these two we will call as slip rings commutator. Okay, slip rings commutator. Okay, because of these two different commutator, it will cause the generator to produce either DC or AC. Okay, DC or AC. Okay, and clear? Good. Okay, no problem here. Okay, so now let us continue a little bit. Let me see here. Okay, so this is how a generator is produced, inducing the current. You see the flowing here. Okay, the turning of the coil, the turning of the coil. Okay, when the coil is turning, it will induce current. The coil turning, it will induce current. Okay, so can you tell me, okay, this one is the coil is in horizontal, like this is in vertical. Can you tell me, you look at these two diagram clearly, this animation clearly. When the coil is in horizontal or in vertical, it will induce current. Horizontal or vertical. Horizontal. Confused. Okay, actually it's vertical. Okay, but why is it vertical? I think I don't really want to continue already, because it will, if let's say I continue, it will stop halfway like that. Okay, so next week I will continue with this application of the electromagnetic induction. Then after that, we will discuss exercise 3.3. Okay, exercise 3.3. So please do exercise 3.3. I think most of it you can do it already, except for if let's say it's about this one, the DC generator and AC generator. Okay, you do most of it. Okay, you do all of it. Okay, those that you don't understand or you cannot do it, then only you put aside. But you need to pass it up to me before. You don't need to pass it up to me. After we discuss, finish everything already, you pass it up to me. Okay, in the Google Classroom. Okay, can? No problem, For this today's lesson, any problem? No problem, Okay, so very good. So I will see you next week for continuing this 3.3 and also exercise 3.3. Okay, discussing exercise 3.3. So please, no need to send in yet. Okay, after I discuss finish already, then only you send it. Okay? Okay, Okay, good. So next week, same time, okay? Same place at your home, okay? 10:30 we will meet. Okay? So you can come in earlier so that we can start earlier. Okay? So you can rest a while, then you can go for your MS class already. Bye. You're welcome. Arigato. Very good. Welcome. Okay, you can leave the meeting already lah.